Here we start looking at the parts of a hyperbola and how they relate. The hyperbola, in my opinion, is the most complex conic section. Lots of parts to it, but once you get some practice, it's really, hopefully, not that difficult to understand. So a hyperbola is very similar to an ellipse, okay? Oops. Very similar to an ellipse in the setup. So you might recognize a lot of this if you've worked with ellipses. The first thing is you start with a center, just like you do with an ellipse. And this is we're going to look at a vertical hyperbola first, and then we'll look at a horizontal next. Okay? So the center. It is our reference point. And we always measure from the center, as you'll see. Measure from the center. Okay, the next thing we have is the transverse axis. Let's see, let's draw that a little better. The transverse axis, which on a vertical hyperbola is vertical. So this is our transverse axis. The transverse axis contains the vertices and the foci. Okay? It is similar to the major axis for an ellipse. Okay, but it's not necessarily remember the major axis of an ellipse is the longest axis. The transverse axis is not necessarily the longest. We'll see that. Okay, so at the ends of our transverse axis we have the vertices. So here's a vertex, and here is a vertex, together making the vertices. The vertices are the endpoints of the transverse axis, and they are on the curve, on the hyperbola curve, which we don't have yet. You'll see that soon. Alright, I mentioned the foci. The foci are on this line as well. The foci in a hyperbola are outside of the vertices. So here's a focus, and here is a focus. So the foci are in line with vertices. They are outside of the vertices. On an ellipse, they're inside. And the curve, as with all conic sections, wraps around the foci. Okay? So a hyperbola, the curve is going to wrap up and down in this case. Alright, next we have to go, so we've got everything vertical here that we need. Now we need the horizontal piece. So let's say this is the horizontal piece, this axis here. This is called the conjugate axis. The conjugate axis is perpendicular to the transverse axis. Okay? And then once we have our transverse axis and our conjugate axis, And you can see here the conjugate axis happens to be longer than the transverse axis. It doesn't have to be, but it can be. Once we have those two axes, that helps us form what's called the center rectangle, or center box is what some books call it, or central box. It has all kinds of names. So we're just going to draw a rectangle using these dimensions that we have, both of these axes that we have. Of course, it surrounds your center, and the edges of your conjugate and transverse axes touch it. Okay, so we have the center box, or center rectangle. It forms around the axes. Okay? Now, what is that useful for? All of this is building up to help us draw this curve, okay? And now, we're getting close now. Our curve is bounded by these asymptotes, these boundaries. So you draw two lines. You draw one line through the corners one way, through the center, like this. So here's one of the lines. And that's an asymptote for this curve. And you do the same through the other corners, through the center. And that's also an asymptote. They're boundaries for the curve. They're X-shaped, always. Boundaries for the curve through corners of rectangle. I should have typed all this. Sorry about that. Alright. Finally, we can graph the curve. The actual hyperbola is not here yet. Notice everything's a dashed line. Now we need to draw the actual curve, which I will make a little thicker to emphasize it. It goes through the vertex, wraps around the focus, and then approaches the boundary, the asymptote. So it starts here. The curve never goes inside the box. Okay? So because it has to wrap upward around the focus. So it comes out, shoots over, and gets really close to this asymptote and keeps getting closer and closer and closer. And same thing this direction. So that's the top part of the hyperbola, and then there's a bottom part that does the same thing, and it wraps downward around the bottom focus. Okay? And that's the actual curve. Let me talk about how to get there again. You need your center. You need to know your distances for your transverse axis, your distance for your conjugate axis. Once you have those, you draw the center box, the center rectangle. Then you draw your X-shaped asymptotes through the center and through the corners of the rectangle. And then you graph through your vertex, approaching the asymptotes. Alright? The foci are not necessary for graphing. The foci are more of a geometrical property of these curves, okay? So you don't actually use those to graph the curve, but they are helpful to tell you that the curve wraps up and wraps down, as we saw here. Okay, let's do this again. Do the horizontal hyperbola. We'll move a little quicker this time. And I'll do this in reverse to help us get an understanding here. I already got all the labels over here. So for a horizontal hyperbola, I'll also try to point out how this is similar to an ellipse. Horizontal hyperbola. Okay, so you need a center first. Then you need your transverse axis. For the horizontal hyperbola, the transverse axis is horizontal, not vertical. So this is our transverse axis. Then we need the vertices, which are the endpoints of the transverse axis. So here is a vertex, here is a vertex. Then we need the foci, which are outside the vertices on the same line as the vertices. So a focus is over here and the other focus is over here. Okay? Then we need our conjugate axis, which runs parallel to the transverse axis. Maybe it looks like this. So this is our conjugate axis. Okay? Then we use the two axes to draw the center rectangle. Okay? Finally, we draw the asymptotes through the corners, through the center. I didn't draw it very well here, but that's the idea. So this is an asymptote. And then we have another one running through the other corners in the center, like so. And that's it. That's the setup. Now we need to draw the curve. And the hyperbola curve in this case passes through the vertices, which are on the left and the right, not on the top and the bottom, and wraps around the foci. So this hyperbola is going to open to the right and to the left. So over here, I wrap around my focus and I approach my asymptotes on both sides. And now our curve, our hyperbola, opens left and right. Okay, very good. So that's an vertical and horizontal hyperbola. Now what are the similarities to an ellipse? In ellipse you start with the center and then you go up, down, left and right, just like we did with the hyperbola. In an ellipse we start with a center, then go up, down, left, and right to get 4 points to make the curve. In a hyperbola, we start with a center, then go up, down, left, and right, but not to get 4 points, to construct the center rectangle. Okay? So that's the difference. In an ellipse, when we went up, down, left, and right using the major and minor axis, you would have a point here, a point here, point here, and point here, and then you would just draw the ellipse shape and you'd be done. But in a hyperbola, you start there, you go up and down, left and right. Your vertices are either left and right or up and down, and then you would construct the box, the rectangle, then the asymptotes, and then the curve to approach the asymptotes. Okay? Now, what is the relationship between all this? Let's go back now. We get three distances. Let's do it this way. We're running out of time, so I'm going to set this up real quick off of the recording. Okay, just like in an ellipse, we have three distances for a hyperbola, A, B, and C. A is the distance from the center to a vertex, okay? So over here, the center to the vertex is a vertical distance, so that's A. And over here, the center to the vertex is a horizontal distance, so that's A. B, let's use a different color. B is from the center to the end of the conjugate axis. So here, the center to the end of the conjugate axis is horizontal, and over here, from the center to the end of the conjugate axis is vertical. Those two together form the center rectangle. Okay? Now, C is not used to graph the curve, but it's from the center to a focus. So here, center to the focus is vertical, and over here, center to the focus is horizontal. These are always, A and C are always measured the same direction. Just like in an ellipse. Okay? Now, what's the relationship between those three things? The equation for those three things is exactly the Pythagorean theorem. C squared equals A squared plus B squared. So if we know two of these distances, we can use this equation to determine the third distance, which is very common. Lots of times you might figure out A and B, and then you'll plug those into this equation and solve for C. Or you might know C and B and plug those into the equation and solve for A. Okay, so that's what this equation is useful for. It's the relationship between those three very important distances. Okay, but the distances are very similar to an ellipse. A is from center to vertex. C is from center to focus. That's exactly the same. And then B is from the center in the other direction. So A and C here are both measured up. B then is measured right. Over here B is measured up and A and C are measured right. Okay, so I hope this helps with hyperbolas, and you're welcome to watch my other videos with examples.